All right, welcome back to Calculus 1. This will be lecture 12 of the course. And in this lecture, we're going to discuss an application of differentiation. Really kind of a handful of lots of different applications, but all of them sort of working in the same way. These are called related rate problems. So we'll discuss using differentiation to find basically the rates of change of two or more related variables, all of which will be changing with respect to time. So we'll be differentiating with respect to time. Okay, so let's jump into it. We'll call this 2.7 related rates. Okay, so for the first example, I'm going to start with a picture. Let's say we have a tank of water and the tank of water just happens to be shaped like a cone. It's going to have a canonical shape. Okay, so that means it's going to kind of look like this. We'll see how good this picture is. It's not terrible. Okay, now so this is the shape of the cone or the tank. It's canonical, and the orientation would be that this would be down. Okay, and so inside here we're going to have some water. Okay, and then the water is going to be draining out of the bottom of the tank right onto the floor or whatever happens to be the case. Okay, so the volume of the tank is going to be kind of the variable of interest here. And actually not the volume of the tank, but the volume of water in the tank. Okay, and so we're going to need a couple of things in order to calculate that. So we're going to start with the radius here. And this is the radius from the center of the tank to the edge of the tank, but specifically at the surface level of the water in the tank. All right. And the other thing we'll need here is the height of the water in the tank. All right, so that's going to extend from the bottom of the tank up to the top. All right. And so the idea here is the volume, which we'll call V, okay, so the volume of the water. So the volume, the radius, the height of the water level, they're all functions of time. So right, if the water is draining out at a certain rate, right, the drainage is, a function of time. And everything's going to be kind of changing in reaction to that, right? So as the water drains out, for example, H is going to decrease, right? And also the radius will decrease as well, right? So all of these variables will be sort of changing with respect to time. And they're all kind of tied together as well. So we got V equals the volume of the water. R is going to be the radius of the water. Well, radius of the cone at the water level. Okay, so the top is the radius of the cone at the water level, right? So up here. Okay, and height, H, is the height of the water. Okay, you can think of really this portion of the cone up here is irrelevant, right? H here is the height of the water, but it's really the height of the relevant portion of the cone. Okay, now all of these things are tied together by the following equation, which you may or may not remember from your geometry. The volume of a cone is equal to pi over 3 times r squared times h. Okay, so the height of the cone times the square of the radius of the base of the cone times pi over 3 will give you the volume of the cone. All right, so this is our sort of key piece of information for this applied problem. Now, what we're interested in, what we'll be interested in figuring out here is what is dV dt, the change in volume with respect to time. right? It's also obviously the derivative of v with respect to t. Okay, so let's just kind of go through the exercise of differentiating this equation right here. And so, obviously, what we'll want to do is we'll want to, because t is not a variable anywhere in this expression, we're going to want to treat this like an implicit differentiation problem. Let me make sure I'm focused here. Okay, so we'll differentiate both sides of this equation with respect to t. So d dt of v equals d dt of pi over 3 r squared h. Okay, so the variables here are v, r, and h. Okay, so differentiating both sides, we would have dv dt over here, and that's going to be equal to, now this is a little tricky. You got to make sure you're kind of clear on what all of the pieces of this expression are. So you've got pi over 3, which is a constant, so we're going to bring that out front. R and h are both variables for which we will be differentiating with respect to t. So what do we got here? We're going to have to use the product rule because we got a product here. So this would be like 2r dr dt times h plus r squared, and then it would just be 1 dh dt. Okay, so just kind of, so here we're differentiating r squared, you get 2r, but it's with respect to t, so it's dr dt, and then the h stays. And then over here, the r squared stays, and we differentiate h, but with respect to t, so it's dh dt. Okay, so let's just clean this up a little bit. So dv dt is equal to pi over 3, and this would be 2r h dr dt plus r squared dh dt. Okay, so here's our derivative. Okay, so from this equation, you can see, right? You can see that the rate of change of v, right? The rate of change of the volume of the liquid is related to the rate of change of the radius and the rate of change of the height, right? So you've got, that's why it's called, these are called related rate problems, right? So all of these quantities are related through this expression, this equation, and the differentiation kind of maintains the relationships, but now these are basically rates of change that are all related in this manner. All right, so what can we do with this? Well, let's assume for the moment that the height of the liquid is 2 feet, right? So at a particular instant in time, the height is going to be 2 feet. And let's assume that the radius of the liquid at the height of 2 feet is 1 foot. Okay, and then if you have that information and you have, and you know the rate of change of those two items, then you can obviously calculate the rate of change of the volume, right? So let's just say here that dr dt is negative 0.1, and these will have to have units on it. This will be feet per minute, we'll say. Okay, and then we'll say dh dt, maybe the height is changing a little bit faster, negative 0.2 feet per minute. Okay, so here's some sort of initial information, and from this we could calculate the change in the volume. Okay, so dv dt then would be pi over 3, and then it's going to be 2 times r will be 1 foot, and I'm going to leave the units in because I think it's useful to see that they all kind of work out. And then h is 2 feet, and then dr dt is negative 0.1 feet per minute. And looks like I'm going to run out of space here, so I'm going to switch down to that next line. And r is 1 foot, and we're going to square that. And dh dt is the negative 0.2 feet per minute. All right. And so we can kind of clean this up here, run through some of these numbers. So this would be 2 times 1 times 2. So you get 4, and then times negative 0.1. So it'd be negative 0.4. Now what's the feet? Feet. That's cubic feet. That's looking good, right? Because we're talking about a volume, so cubic feet would make sense. And then over here you've got 1 foot squared times negative 0.2 feet. So that's going to be negative 0.2 feet cubed per minute. And so it looks like you get something like pi over 3 times negative 0.6 cubic feet per minute. And of course you can multiply that out. And ultimately, when you do that, you get negative 0.942 cubic feet per minute. That's a 3, not a B. Okay, so and of course, you know, this rate here is based on, you know, an assumption regarding how quickly basically the water level's changing. So given the difference, given the way that the water level's changing, can you calculate the rate of change of the volume? Yes. Okay, so there we go. First example of related rates. Okay, let's do a couple more examples. Here's another one. This will be a little less involved. Suppose x and y are both differentiable with respect to t. So suppose x and y are both differentiable with respect to t, okay, and are related, okay, so these two quantities are related by the equation y equals x squared plus 3. Okay, let's find dy dt. Okay, when x equals 1, given that dx dt, given that dx dt equals 2 when x equals 1. Okay, so that's a little bit wordy, but suppose x and y are both differentiable with respect to t and are related by the equation y equals x squared plus 3. What we want to do then is find dy dt when x is equal to 1, given that the derivative of x with respect to t is equal to 2 at that time. Okay, so this is kind of like an even simpler version of the previous example. So y equals x squared plus 3. Let's differentiate both sides with respect to t. Okay, we can do that just like so. And we would have, let's go through this. So you'd get dy dt over here, and that's going to be equal to, well, this could be pretty simple, right? So it's just going to be equal to 2x dx dt, right? And then the 3, of course, is 0. Okay, so there we go. And then we've got our values to plug in here. X equals 1, dx dt equals 2. We're interested in dy dt. And so dy dt at those values would be, you could just kind of plug everything in here, 2 times 1 and then times 2, so it's 4. Okay, so this is a unitless problem here, so that's not a problem. All right, so like another kind of simple example of this related rates idea. All right, so you've got some expression, and you want to know how a particular quantity, what the rate of change for one of these quantities is going to be with respect to time, given all of the other quantities and their rates of change, right? And so that's kind of the name of the game with these related rate type problems. Now here's a tricky one. So I'm going to read the problem first, and then we'll draw some pictures. A pebble is dropped into a perfectly calm pond. Okay, so the pebble is dropped in from above. This causes ripples to form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the rate of increase of the area of the disturbed water? Okay, so you've got some kind of a lake here, right? And you drop a rock into the lake. Okay, and when you drop the rock into the lake, it hits, kind of splashes in the middle. And what starts to happen is you start to get these ripples. These are obviously not properly drawn. Right, but they're ripples of concentric circles that, are based on the wave pattern that's forming on the water surface. Okay, so what we're interested in is there's going to be a series of these waves, but what we're interested in is the outer wave, right, which is kind of this distance out to here, right? And we'll assume that this would be symmetric. I didn't draw it very well, but let's just assume that this is a circle, right, because you're dropping it straight from up above and it's perfectly calm. So, okay, so there's going to be some radius r here of this outer ripple. Okay, so the question is, so the assumption here is that the radius r here is increasing at a constant rate of 1 foot per second. So r is increasing at a constant 1 foot per second. Okay, so that's kind of the given information there. And the question is, when the radius is 4 feet, what's the rate of increase of the area of the disturbed water? Okay. Pardon my handwriting is just horrible there. So theoretically, like, the disturbed water is just going to be represented by this outer ripple, right? Everything out here is undisturbed, right, until the outer ripple reaches it, right? And so if the radius of this ripple is increasing at a constant rate of 1 foot per second, when the radius is 4 feet, what is the rate of increase of the entire area of the ripple, of the outer ripple, of the disturbed water? Okay. All right. Well, so that's obviously going to involve the idea of a circle, right? The area of a circle, right? So this outer ripple is basically a circle. And so the area of a circle we know is pi r squared. Okay, so this is the area of a circle. Okay, and that's going to be the sort of unifying equation here. And so what we want to do is we want to differentiate this equation here with respect to time, with respect to t. Okay, so differentiating both sides by t, we would get dA dt on this side, and and we'll just write it first, and then we'll actually calculate it. ddt of pi r squared, and then again pi is a constant, so it comes outside, and then you're going to have 2r dr dt. Okay, so we might be able to clean that up and write it 2 pi r dr dt. Okay. All right, so that's the equation. All right, that's the differential equation. dA dt is equal to 2 pi r dr dt. All right, and so the question here is, is when the radius is 4 feet, namely when r is 4 feet, what is the rate of increase of the area? So what is dA dt when r is 4 feet? Well, we know also that the rate of change of the radius is constant 1 foot per second. So we can just plug all this in, can't we? So dA dt would be equal to 2 pi times r would be 4 feet, and dr dt would be 1 foot per second. Can we multiply all that together. Yep. So we'd get what, 8 pi feet squared per second. Okay, and so that's approximately, if you do the math there, it's like 25. I'll just put approximately 25 square feet per second. Okay. All right. So there you go. That's another example of a nice related rate problem. Okay, good. So this is super useful, super important math for physics and engineering. This kind of stuff is sort of the bread and butter of a lot of engineering. Let's focus this a little better. Let's do an example here. It's not focusing. There we go. Okay, so let's do one more example. So let me read the example. So air is being pumped into a perfectly spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Okay, so I don't know if we need a picture, but I'm just going to draw a picture. So we've got this perfectly spherical balloon, right? So remember, this is a sphere, so it's three-dimensional, right? And then this sphere is going to have some kind of a radius, like that. Okay, and this is a balloon, so it's got this little balloon thing on the bottom, and there's, you know, some kind of like air hose pumping air into the balloon. Okay, and so obviously the balloon is expanding at a certain, you know, rate. Okay, all right, so there's our picture. Okay, so what do we know? Let's write the facts down here. The air is being pumped into the balloon at a rate of 4.5 cubic feet per minute. 4.5 cubic feet per minute. That's the rate at which the air is coming into the balloon. Okay. Okay, so we've got that piece of information. And what we're interested in is we want to know what is the rate of change of the radius. When the radius is 2 feet. Okay, so when the radius expands to 2 feet, what's the rate of change of the radius? So how fast is it expanding? All right, so this is a sphere. This is a sphere. Okay, so we need the area of the sphere. So the area of a sphere is, oh, sorry, not the area, the volume. The volume of a sphere is 4/3 pi r cubed. Okay, so you take the radius, cube it, and multiply by pi and 4/3. Okay, and that is your volume. Okay. Okay, so this is our expression, and we're going to differentiate this with respect to t and solve this and answer this question regarding the rate of change of the radius. So dv dt will be equal to d dt of 4/3 pi r cubed, which would be 4 pi over 3 times, now so pulling those out, and it's going to be 3r squared dr dt. And that's just the derivative of r cubed with respect to t. All right, and so let's just clean this up a little bit here. So we would have dv dt equals, the 3's will cancel, so you'd have 4 pi r squared, and then dr dt. Okay, so that's sort of that's kind of the best, cleanest version of the expression. So we're asked to identify the rate of change of the radius at the moment when the radius is 2 feet. Okay, so let's just figure that out quick. So dv dt would be equal to 4 times pi. Now the radius is going to be 2 feet. and that's squared. And then dr dt. Okay, so let's see here. Okay, all right, so we've got this. Okay, and so what we're actually interested in here is dr dt, right? Okay, so what we need to do a little bit of algebra to get dr dt by itself. Okay, and so basically we would just need to divide by this piece here. So let's flip all of this over and kind of combine some of this. This would be 4 times 2 squared. All right, so this would be, so on this side you still got your dv dt, and then you've got 1 divided by 16 pi feet squared. Okay, and that's going to be equal to dr dt. Okay, looks good. And so let's see here. So we're looking for this, right? We know this, right? Remember, this was a piece of information that was given to us very early on here. In particular, we know that the rate at which the air is coming into the balloon is 4.5 cubic feet per minute. And so we can plug that information in for dv dt. This is the rate of change of the volume with respect to time. And so instead of 4.5, I'm going to use 9/2. And so dr dt is equal to, and then let's switch the order here. And then dv dt is going to be 9/2. I'll just leave it at 4.5. 4.5 cubic feet per minute. Okay, oops. Okay, so here's our expression right here. And then we just have to crunch all of these numbers, right? So basically 4.5 divided by 16 pi. And when you do all of that, now notice the feet will cancel, right? You got a feet squared here, feet cubed there, that'll cancel. And when you do all of this, when you plug all of this in, you get something like 0.9 feet per minute. Okay, and that, so this is the, so 0.9 feet per minute is the rate of change of r when r is 2 feet. All right, so it's the instantaneous rate of change of the radius of the sphere at the exact moment, right? The instantaneous rate of change at the time, at the moment that the radius is equal to 2 feet. Okay. Interesting, powerful, powerful application here. Right. So this is, I remember when I first went through this material in Calculus 1 when I was an undergraduate. This is very compelling use of differentiation, right? So all of these old volume formulas that you may recall, all of the area formulas, all of the geometric formulas that you've encountered over your years studying math, now have a new potential applications, right? So now you can start to take those geometric formulas and, you know, clothe them in these sort of interesting applied situations, like spherical balloons blowing up at a certain rate, or, you know, cylindrical or canonical, you know, water tanks, you know, with water dripping out the bottom. Or, you know, another one that's very common is like, that we didn't talk about here, would be like cylindrical, you know, tanks, right? That, you know, there where water's coming in at a certain rate and going out at a certain rate, right? And maybe those two rates change, and as those two rates change, maybe the water level, you know, drops or increases or something. And so these kind of problems that can all be sort of summed up, where the relationship of the various quantities can be captured by some kind of an equation, geometric equation. You can, they kind of come to life now with this differentiation stuff. So, okay. All right, so that is it for this section. And next time we'll start talking more about applications of differentiation, and in particular we'll kind of enter into a series of lectures where we're going to be able to break down all of the minutiae of detail regarding graphs of functions, and all of the detail that we can derive from them using derivatives. And so we'll get into a series of lectures on additional applications of differentiation. We'll see you then.